Right, and finally, it's time for AP Physics 2. This is the last one. Once again, my brand, World Finest Physics. If you are parent, student, interested in tutoring, I know it's after the AP exam now, but you might be taking math or physics next year. You can reach out to me there. Or if you're a physics or math teacher who might be watching this, or if you're a physics teacher who wants to let math teachers at school know about our professional development offerings, then you can see them there at findphysics.com. And that sound means that class has started, and this is my off period, so I'm just going to go ahead and record these. Okay, so these were released yesterday afternoon. I did pull them up on my phone and just kind of had a little look at them. I didn't look too closely at them, so this is a little rehearsed, but not entirely. Let's have a look here. In each trial of the photoelectric effect experiment, scientists use a device to shine light at a single frequency on two different metals, 1 and 2. Device can emit light with frequency ABC. Each frequency is used to test both metals. So it looks like we have a table here. The scientist determines the minimum de Broglie wavelength of the electrons ejected with material. The following table summarizes the results of the experiment for each trial. And the scientist analyzes only the electrons with the maximum minimum wavelength, which is the maximum speed and momentum and energy. Okay, so we have this table here, okay, and it says, in a coherent paragraph length response, indicate which frequency is the greatest and which frequency is the least. Justify your answer in terms of physics principles. Okay, so the lowest, let's see here. So the greatest frequency is going to be C, because the lowest wavelength, then A, then B, because there's no electrons ejected at all. So frequency C is greater than frequency A is greater than frequency B. And I'm going to make the following remarks. I'm going to say, okay, so a shorter de Broglie wavelength means more momentum. Momentum is h over lambda, right? Okay, so more momentum of an electron, more kinetic energy, right? Kinetic energy is p squared over 2m, or it's, p equals mv and k equals 1/2 mv squared, right? Okay, all right, so then more kinetic energy results from higher frequency photons, right? So K equals HF minus the work function, right? So I'm going to say this. Frequency C results in the shortest wavelengths, then A, okay? But B is such a low frequency that HF is less than the work function, so electrons cannot be ejected. Okay, all good. Calculate the maximum kinetic energy of the electrons ejected from metal 1 in trial 1. Assume that the momentum of an ejected electron can be described by the classical definition. In other words, not relativity. All right, that's what it means. It's not going relativistically fast. So the maximum kinetic energy of the electrons ejected from metal 1 in trial 1. Metal 1 in trial 1, the wavelength is 6.9, 10 to the negative 10. So the wavelength is 6.9 times 10 to the negative 10 meters, and momentum is equal to h over the wavelength. I can never get h memorized. I'm sorry. It's 6.63, 10 to the negative 34, okay? So then this is going to be 6.63, 10 to the negative 34 divided by 6.9, 10 to the negative 10, okay? 6.63, 10 to the negative 34 divided by 6.9, 10 to the negative 10. I think it was 10 to the negative 10, wasn't it? Yes, okay. So I've got 9.61, 10 to the negative 25, 9.61, 10 to the negative 25. We're going to set that equal to mv of an electron. Okay, so the m of an electron is 9.11, 10 to the negative 31. So then the speeds of the electrons, 105 basically, meters per second, which is way less than 1% of the speed of light, so I'm not concerned. And then now I'm going to say the kinetic energy is 1/2 mv squared, so that's going to be 1/2 m that velocity squared, and I'm going to get the kinetic energy to be 5.067 10 to the negative 19 joules. Okay. Indicate whether the work function of metal 1 is greater than, less than, or equal to the work function of metal 2. Ooh, I like that question. That's a good question. Okay, so let's have a look here. So electrons from metal 2 have longer wavelengths, and so they are going less speed. Electrons from metal 2 have longer wavelengths, so they have less momentum, less speed, less kinetic energy, right? Momentum is h over lambda, momentum is mv, kinetic energy is 1/2 mv squared. So longer, less is less, and less is less, right? Now, kinetic energy equals hf minus the work function, and hf is the same in each trial. So if 2 has less kinetic energy electrons, then the work function is greater for 2 because it subtracts more. It's going to subtract more from the HF. Oh, good. That's the end of that question. Okay, we're just moving right along here. In experiment 1, shown in figure 1, a sample of an ideal gas is contained in an insulated, sealed container chamber with thin walls. Okay. Rigid. Rigid is going to be important. I can't change the volume. The chamber contains a heater and sensors to measure the temperature and pressure of the gas. Student is asked to design an experiment to determine the number n of molecules in the gas contained by the chamber. Okay. Describe a procedure for collecting data that would allow the student to determine an experimental value for n. Okay, so here's what I'm going to do. Turn on the heater and take readings of temperature and pressure every 10 seconds for 47 days, or just for some amount of time. Okay, I'm making a joke here, right? Okay. And then the next thing I'm going to do is also hold a meter stick up to the chamber to measure its length, width, and height. And I'm going to say this: calculate volume V as length times width times height. So I guess the reason that the walls had to be thin was so that this length and this length are almost the same, because you can't measure the inside without letting the gas out, okay? So you have to measure the outside. Okay. On the following axes, sketch a curve or line to represent the expected relationship between the pressure and volume of the gas. The pressure and volume of the gas while the heater's turned on. The volume can't change. All right, so the pressure would go up. The volume can't change. On following axes, sketch to represent the expected internal energy. Draw an arrow on the line or curve or line to represent the direction. It's the same. The internal energy is 3/2 PV nRT NKT, right? So 3/2 of the ideal gas constant. So this can't change, and this is going up, up, up as the temperature goes up, up, up. Okay, whatever. Why the curve or line drawn part B2 has the shape you sketched. U equals 3/2 PV. P increases as the temperature increases, but the volume can't change if the container is rigid. All right. Okay, in experiment 2, a liquid-filled container is completely wrapped in with a material of uniform thickness 0.1 meters. is inside the sealed container chamber that's filled with ideal gas. The material has total area of 0.06 because, okay. I guess that's for the 6 faces of the cube. In contact with the gas. So the area of one face is 0.1, the area of 0.01. So, okay. So each side is 0.1 meters. Each side is 1/10 of a meter. I'm not sure if I really need to know that. I'm just trying to figure this out. And it's 0.01 meters thick. So it is 1/10 as thick as it is wide. Okay, I believe that. All right. The heater's turned on as the temperature of the gas increases. The following data for the temperature of the liquid and the rate that of the energy transfer are collected. So we have the temperature of the gas, we have the temperature of the liquid, and there's no energy transferred. The student is asked to determine an experimental value for the thermal conductivity K of the material used to wrap the cylinder inside the steel container. Okay, there's no task here, but I'm going to just write this. Delta Q over delta T. I call it delta Q over delta T. I can't stand the Q over T. I know the Q is a change, but it's delta. It's a couple of deltas and everything. It's the way differentials work. So K area. Now, this delta T is tricky because students think it's a change in temperature, but no, it's actually a difference between two temperatures. So I try to avoid saying the delta T because they think that the temperature is changing somehow, like in the specific heat formula. And then this is the thickness right here. Okay, so what I'm imagining is that these are constants, and I need to just graph delta Q over delta T versus the difference between the temperatures. Okay, so, all right, indicate what measured and or calculated quantities could be graphed. On the vertical axis is going to be delta Q over delta T. I better use the same symbols they use, Q over T. And on the horizontal axis, it will be T gas minus T liquid, okay? So now I need to fill in T gas minus T liquid, okay? So 0. 68. I really should be using my calculator for this. I don't trust me to do this correctly. 371. Actually, you know what? I'm really lazy, so let's just do this, okay? 295. 371, 425, 475, 528, 528, okay? And then this can be 295, 303, 308, 313, 323, okay? So now this is going to be L1 minus L2, and then we're going to have 0, 26.3, 43.1, 60, 75. Okay, so this is going to be 68, 117, 162, and 205. Okay, so let's make sure I do this correctly. Okay, I think that we're going to do T gas minus T liquid here, which is going to be in this kelvins, degrees Celsius. It actually doesn't matter. It'd be the same. I wonder if the readers are smart enough to figure that out. If this says degrees Celsius, it still works out. Okay, and then this is going to be Q over delta T, joules per second, or watts. They would be smart enough to figure that out, by the way. I have full faith in them for that one. 50, 100, 150, and 200, and 250. And then what am I looking at here? 75. So 25, 50, 75, 100. That's as much as I need there. So 0, 0 is definitely a data point. We also have 68, which is almost 70, and 28.3, which is going to bring us to about right there. And then 117, 117, and 43.1 takes me to about right there. And then 162 and a hard 60 right there, maybe. And then 205, which is right in between, and 75, which is about right there. Okay, draw a best fit line. You want to always have an equal number of dots above and below, maybe at least one dot above, one dot below. And the other thing you want to do is you want to make sure that you don't force it to go through the origin if you don't have to, although it looks like it really wants to go. I calculate an experimental value for K. So what I'm going to do is I'm going to use my linear regression on my calculator. I'm going to say the slope is 0.365 from TI 84 linear regression. Yes, please write that if you use linear regression. Otherwise, you should put 2 open circles and calculate the rise of the run of them. So if I did that, it would have been, what is this? 5 to 90. So 85 over 250. And I got 0.34 as a point to point three opposed to 0.436. So whatever. Okay. So I have Q over delta T equals Ka T minus T, gas, liquid, over L. So now I'm going to say Q over delta T is the rise, and T minus T is the run. So then Ka over L is the slope. So I'm going to take my 0.365. I'm going to set it equal to K, the area 0.06, and the L 0.01. That was the thickness, and that was the total area. So that's basically 6. So I'm just going to divide this by 6, okay? And then the K I get is 0.0567. Okay. Q over T equals Ka delta temperature over L. So this is going to be joules over seconds equals K meters squared Kelvin over meters. Okay. So joules per meter seconds Kelvin. Okay. Joules per meters seconds Kelvin. I think that's the units for thermal conductivity. I was about to say spring constant. Okay, remember, numbers, always put units on them. Okay, let's see. Circuit consists of EMF E and 4 identical resistors, which do not get italics. Oh, that's the name of the resistors. Oh, here's a style guide for you. The names of objects are not italicized, but variables are. So there you go. Okay, E and R only. Derive an expression for the current I1 and resistor R1. Okay, so here's the only way to do it is to first get the equivalent resistance, which is going to be this. You're going to have the R, I'm going to say R1 is in series with the following complex, R2 and R3 and R4 in parallel. So then you're going to get R plus 1 over R plus 1 over R plus 1 over 2R basically. So then this is going to be R plus, this is going to take a lot of time. Okay, this is going to take up a lot of space just getting the R equivalent. 2 and 2. So that makes 3. So this is 2/3 of an R, I think. 2R over 3. So then this is going to be the R equivalent is going to be 5R over 3. I'm going to just check that. Wait, 1 plus 1's reciprocal plus 2's reciprocal reciprocated. Yeah, it's 5/3. Okay, so then, okay, so that's step 1. Step 2, the I of the battery is the EMF over the R equivalent, which is the EMF over 5R over 3. So that's going to be 3 EMF over 5R. That's the I of the battery. And then step 3, the I of 1 is equal to the I of the battery because they're in series. So that is the current that they're asking for. Derive an expression for the current I3 through in resistor R3. Okay, so for this one, what I'm going to do is I'm going to do what I call the method of shares. What do you mean when you say that? Well, here we have 1R and here we have 2Rs. That's the 2 branches that this current is going to go into. So the current in is going to go into R and 2R. Now the volts have to be the same. So that means that the IR on the left has to equal the IR on the right. Now listen to my reasoning here. If the right side has twice the resistance, then the left side has twice the current. So the resistances are a 1-to-2 ratio. So the currents have to be a 2-to-1 ratio. So I'm going to take the current in and I'm going to split it into 3 pieces. 2 plus 1 is 3. This is where 2/3 of the I in is going to go. And this is where 1/3 of the I in is going to go. Okay, do you see that? So with this input, with this being twice, I'm just going to split the current into 3 pieces. You get 2, you get 1. So you get your 2-to-1 ratio. Okay, so I'm going to make the following. I'm going to say since R3 and 4 is equal to 2R and R2 is equal to R, the current in the 3 and 4 branch is half the current in the 2 branch. Okay, so the current in 3 and 4 is 1/3 of the current through 1, and the current through 2 is 2/3 the current in 1. So I'm making this kind of qualitative argument, you know. So I'm going to say this: the current in 3 and 4, which is the current in just 3, is going to be 1/3 of 3e over 5r, which is going to be E over 5r. All right, so that's the current right there in resistor 3. Okay, blast. Okay, so the partly completed bar chart in figure 2 shows a bar that represents the potential difference across the battery. Draw a bar to represent the potential difference across each resistor relative to the EMF of the ideal battery. So the story is going to go something like this. Was this 5 bars? I bet it is. 1, 2, 3, 4, 5. Yeah. So what I'm going to say is I'm going to make the following remark. I'm going to make this remark that this is 1I, I being EMF over 5R, which is EMF over 5R, right? This is going to be 2 I's, and this is going to be 3 I's, okay? Now, V equals IR, so then that means if they're all the same R, this is 3 voltages, 2 voltages, 1 voltage, and 1 voltage. So then this is going to be 3 voltages, 2 voltages, and now you see we obey the loop rule for the battery 1-2 loop. The battery 1-2 loop, gain 5, drop 3, drop 2. Okay, now for the other loop, which is the battery 1-3-4, for the battery 1-3-4 loop, we now have the battery gain 5, drop 3, drop 1, and 1. So that still works out. Okay, student claims that the rate at which energy is dissipated, also known as power, can be expressed as that. State whether the expression for P is correct or incorrect. So I'm going to say, well, here, power is I squared times R, and for resistor, I'm sorry, I did not mean this. Let me try that again. Power is I times V, and for the entire circuit, comma, I is the I of the battery, and V is the EMF of the battery, right? So I'm going to say P equals I. What was the I got for the battery? 3E over 5R. 3 EMF over 5R, and then that's the I and that is E. So then I do get 3 EMF squared over 5R. So this is correct. Referring to the derivations from part A or the bar chart from part B. Well, I used the derivation from part A. I think I would have gotten full credit for that, don't you think? All right, when the ideal battery is connected to the original circuit, the power is P original. The ideal battery is replaced with a new one that has internal resistance. The rate at which energy is dissipated is P new, which is less than P original. Justify your answer. I'm going to say this. I'm going to say the R equivalent of the circuit, not including little r, is the same, but adding the little r increases the R equivalent of R and R1 and R2 and R3 and R4, right? So the current from the battery is less, right? Current equals EMF over R equivalent. This went up and this went down, right? But I, the battery, is also I for resistor 1. Power is I squared R. R is the same. I is less. It did say briefly. This is not brief at all. I'm sorry. Maybe briefly it was, well, there's less current, so there's less power. Something like that is what they really want to hear. So less power. Yeah, briefly is like, we really don't have to write an essay. All right, last one. Two particles, 1 and 2, have different mass and charge described by the following: M and Q, half of M and 2Q. In separate trials, a device is used to accelerate each particle from rest or potential difference. Now, let me understand this clearly. If you say accelerate through a potential difference, do not let the word accelerate confuse you. This is not Newton's second law. We're going to say Q delta V equals 1/2 mv squared, or you could say Q delta V is equal to the amount of kinetic energy, okay? The polarity of the potential difference, it can be adjusted so the particle with either positive or negative charge will accelerate in negative y direction. Gravitational effects are negligible. After moving through the potential difference, particles 1 and 2 exit the device kinetic energy to K1 and K2. Calculate K2 over K1. Okay, so K2 is going to be charge 2 delta V, and K1 is going to be charge 1 delta V, and the delta V's are the same, right? Because the kinetic energy comes from the potential energy. So really, this is Q2 over Q1, and it's the absolute value of it because they can change the polarity and kinetic energy can only be positive. So Q2 is 2 Qs, Q1 is 1 Q, so 2. Okay. After exiting the device, the particles enter a large region of uniform magnetic field, B naught, that is directed in the positive Z direction out of the page. Each particle is moving in the negative Y direction when entering the region. Each particle is moving in the positive Y direction exiting the region. Great. Determine an expression for the speed of particle 2 in the region. Express your answer in terms of M, K2, and physical constants as appropriate. Well, K is 1/2 mv squared. K2 is 1/2. What's his mass? M over 2 v squared. So then K2 is just M over 4 v squared. So 4K2 over M is equal to v squared. So squared, is that all you wanted? Okay. Derive an expression for the horizontal distance delta x between the locations where particle 2 enters and leaves the region. Say this in terms of all that. Interesting that they said derive here, but they didn't put their little tagline. Start with a basic equation of physics or equations from the reference booklet, right? They didn't do that this time. And you notice this is a determine and this is a derive, and yet I'm doing the same thing. So is determine like just give me the answer? I don't really need to see the work. Derive definitely means we need to see the work. So the force QVB is going to equal mv squared over r, okay? And the delta x is a diameter, so it's going to be 2r's, okay? Now, the v's partially cancel. Oh, what is the q of particle 2? The q of particle 2 is 2q. I better get that right. Okay, 2q times b naught. Let's use the correct subscripts here. And this is going to be the m of particle 2 is m over 2. So really m over 2, okay? V is that. I'm going to plug that in later. I don't feel like plugging it in right now. We're R. So then the R is going to be mv over 4qb naught. And now I need to do this. I'm going to say that delta x is double R, which is 2 m over 4qb naughts. And then I'm going to put in the V, 4k2 over m. And this is technically correct, but it turns out this is 2 and 4 all cancel. And then the m can partially cancel. So you actually get the square root of m, capital M times K2 over Q B naught, I think is the delta X. Okay. Anyway. All right. On the following diagram, sketch and clearly label the paths of both particles 1 and 2 in the region. Okay. So what do I know about particle 2? He's positive. So particle 2 is going to get forced to the left, and particle 1 is going to get forced to the right. Okay. So you, by the way, I don't know if you care. Motion of the charge, magnetic field, force. I use the gun rule. Okay. And my gun is the motion of the charge, the magnetic field, and the thumb. That's how I do it. Okay. So we know that I think I just said particle 2 is going that way and particle 1 is going that way. Let me double check my references here. Okay. So what I really want to do is I want to say if QVB equals mv squared over r, then QB equals mv over r. So then let's see. Oh, wait a minute. Okay. Let's see. I need to use my derivation from before. Okay, I'm sorry. Give me a second here. Okay, so now I'm going to square everybody. Q squared, B squared. I really shouldn't have to redo this work, but for some reason I need to redo this work. Okay, so then I'm going to say R squared equals M times MV squared over q squared b squared. And I'm going to put a 1/2 here and a 2 here. So then r squared is 2mk over q squared b squared. So r is the square root of 2mk over qb. Okay, so now here's what I'm trying to understand from this. The b is the same for everybody, and so is the k because they were shot out of the same potential difference. For particle 2 has half the mass and twice the charge. So having half the mass and twice the charge, he is going to have a much lesser radius. So then I am going to say that particle 1 is going to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's make him 4. Okay, so he's going to go over 4. So then 1, 2. Let's make it a really nice circle here. Okay, so here is particle 1. Is going to go that way, I think. And then particle 2 is going to have, what is 1 over the square root of 8? Okay, so he is going to go only a diameter that is, hold on a second, a diameter that's 1.4. So 1 and 0.4 is going to bring him about here. So then, like that. Yeah, I did do this pretty precisely. Okay, I hope I did this correctly because I'm not entirely sure of myself now. A uniform electric field is added to the region such that particle 1 of negative charge, negative q, travels at constant speed in a straight line through the region. Determine the direction of the electric field. Okay, so the magnetic force on 1 is that way, and the magnetic field is out of the page, the velocity is down, and the charge is negative. So let me just double check that that is the way that it was supposed to be. So that means, so I'm going to say if FB is right, FE is left, right? Okay, so then the electric field force has to be the right. If electric force is to the left on a negative, the electric field is right, so E points to the right. It did not actually say to explain my reasoning, though. So, that's the end. All right, well, that's the end of AP Physics for this year. And the end of this particular exam format. We have a new exam format rolling out next year that is uniform across all 4 AP Physics exams. And the P1 and C Mechanics share a whole lot of learning objectives. And P2 and CE Mag also share a lot of learning objectives. So we'll see what that looks like and feels like.